Let me give you some of the papers that we've covered so far. I've been looking at median and center problems, the single facility case, and we have actually covered a bunch of results. And if you want to find details, you may want to look at the following papers. The first paper that posed the absolute median and center problems is Hakimi's 1964 paper. We haven't gone into the multi-facility case, but there's a subsequent paper published in 1965 which covers the multi-median case and multi-center case. But that will come later. Goldman, in his 71 paper, also a related paper is his 72 paper, looks at the medians of trees. The tree trimming algorithm, if you remember, that's the one he actually solved. And next, Deering and Francis. '74, Goldman. '72, Halfen. '74, Handler. '73. These are on absolute centers of trees. The paper by Francis Lauer Ratliff, 1978, that's on distance constraints, a special case of which is the single facility distance constraint, and the neighborhood problem and the composite neighborhood representation algorithm. That comes from this paper. So that stuff, of course, relates to the absolute centers of trees again. So it belongs here as well. But the recognition form of the problem is the one under consideration with fixed z. The paper by Francis in '77, that's the nonlinear one-center problem, which I haven't covered yet, but I plan to. It's a nice generalization of the linear one-center problem. And finally, you've got, let's see, Deering and Francis, '74, and Deering, Francis, Lauer, '76. The initial stuff I gave you on embeddings of networks, you can find information on that in both of these papers. The second one is a highly theoretical one on convexity, but you might want to actually look at it for also the embedding portion. Okay. I'll give you a list of papers as we go along. These are, you might think that they're old papers, but they cover the foundations. Once you've got the foundations well conceived, then everything actually comes much easier. There will be eventually integer programming approaches which are more standard material, but these are material which actually work directly with the network of interest, and that gives you much deeper insights about the problem than standard integer programming approach. All right, so where are we left last time? We looked at the neighborhood, composite neighborhood representation, and I gave you a theorem which says that, well, there were actually two theorems. The property number 9 was if you reduce each radius by some epsilon amount, then the composite neighborhood is also shrunk by the epsilon amount. And that actually had an interesting corollary, that the composite neighborhood representation, using the algorithm I gave you, is order invariant. It doesn't matter in which particular order you actually intersect the pairs of neighborhoods. Okay, now we can switch back to the minimax location problem. Everybody got this? Because I'm going to put this down. So, we had actually started out with the discussion of the absolute one center of trees. We sidetracked, we looked at the neighborhood material, and now we're back to the absolute one center. So we're trying to minimize f of x, x in t, where f of x is the maximum of weighted distances from x to each vertex vi plus an addend I. And we're trying to minimize the maximum of these quantities. Okay. The equivalent problem is to minimize a variable z subject to f of x being less or equal z. But f of x is less or equal to z if each term that defines or that appears in the maximum operator is less or equal z. So this amounts to requiring each distance to be less or equal z minus ai divided by wi. I'm assuming wi are positive numbers here, otherwise of course the division will not occur. Well, actually you can take division by 0 to be infinity, in which case this is automatically satisfied, okay? The distance is always less than infinity. Okay. With x restricted to 3. I gave you necessary sufficient conditions for distance constraints to be consistent or to admit a solution for a given Ri or upper bound on the distance. What property was that? Does anybody remember? Was it property 6? Yeah, the neighborhoods. Here's the property. The neighborhoods have a non-empty intersection if and only if every pair of neighborhoods has a non-empty intersection. If and only if the distance between any Vi and Vj is less or equal Ri plus Rj. Remember that? Property 6? Okay. Necessary and sufficient conditions of property 6 imply that the constraints, let's call this P0, the constraints of P0 admit a feasible solution x and z, x in tree, z in real, T cross R. It's not an x, it's a cross product. Okay, admit a feasible solution x and z if and only if what is true? The distance between every pair, so distance between Vi and Vj is less than or equal to the sum of the upper bounds associated with those pairs of indices. So z minus ai divided by wi plus, that's the one associated with the ith constraint here, okay? And I'm going to also look at the jth constraint, and we add them up. The jth one, z minus aj divided by wj. This should hold true for every pair I and j. Because of symmetry, we don't need to look at all, but I less than or equal j is enough. Okay. So, if and only if actually z satisfies, because there's no x here. If and only if z satisfies these conditions, okay? So the idea here is to pick the correct value for z such that these conditions hold so that there's a feasible x for that particular choice of z. Accordingly, we want the minimum z such that the constraints here actually, let's number it this way. 1, 2, 3, 4. Accordingly, we want the minimum z such that 4 holds. That's what we want. Because if 4 holds, then I will be able to find a point x. And I'm looking for the minimum z because that's what I'm trying to do in the minimization problem P0. Okay. So 4 holds if and only if, let's just manipulate this a little bit. Distance Vi, Vj is less than or equal to, this is simply z over wi
plus z over wj here, so it's 1 z into 1 over wi plus 1 over wj. And then you've got also minus ai over wi plus ai wj. Which is true if and only if, now I just take the constants in the second parentheses to the left side. And then that leaves z times this sum of the reciprocal weights on the right. So if you divide by the sum of the reciprocal weights, you're requiring z to be bounded below by that. Everything is non-negative here, so the inequality does not reverse. Okay? If and only if this is true for I less than or equal to j less than or equal to n. Now, this is, of course, familiar to you, right? That's the alpha ij that I defined before. And it turns out that there's a natural way that it comes out, actually. All right. To be the left side of 6. So defining alpha ij to be the left side of 6. Maybe I should put this up one more time because the camera may not see it. So, okay, so that's number 6. Well, z is required to be greater or equal each alpha ij, so z is greater or equal the maximum of these alpha ij's. And since you're looking for the minimum such z that permits feasible solution, of course, the minimum z is obtained by equating, okay? So I know how to compute the optimum objective function value of the minimax problem by simply computing my alpha ij's and taking the maximum. Now, are alpha ij's computable using the data of the problem? They are, because the only thing that they involve is vertex to vertex distances plus the ai over wi values for vertices plus the sum of the reciprocal weights. So everything is on hand, and optimum value z star is computed. So once your Z star is available, all you have to do is you're looking for the intersection of neighborhoods. They are centered at each VI. The upper bound is how much? Where's the upper bound? The upper bound is here in P0. That becomes your Ri with the fixed value of Z at Z star. Okay? So you set this equal to Z star, and you take that to be your Ri. So that's what I'm going to write down here. And VI, Ri, which is actually Z star minus AI divided by Wi. So your radii are defined by these numbers. The intersection is from 1 to n. And if you compute the composite neighborhood representation for this, it will output a neighborhood with some center and some radius.
Radius should be 0.
Good. Why?
Otherwise we can still shrink.
Yes. The radius should be 0. It will give you a point, whatever that point is. Let's just call it x star. So this will indeed be a unique point, which is one question that John had raised. So the answer is yes, it is a unique solution. If the composite neighborhood does not have a radius of 0, that means Z star here can be, in other words, each radius can be a little bit reduced by some epsilon, by positive epsilon, so that you still have a feasible solution, which is defined by whatever radius you have here minus that epsilon. And of course, that would imply that the Z star you computed is not actually the minimum. There's something better than that. But of course, by construction, there's nothing better than that. Because if you go below that, you will actually violate at least one constraint. Okay, so this should be the solution.
Is this optimum value also valid in general graphs?
No. What fails in general networks? What is it that fails in general networks? The neighbor, yeah, the necessary and sufficient conditions of property 6 are not valid for general networks. They are only valid for tree networks. That's why the result will fail there. Okay? But you might recall that for general networks, when you compute the maximum value here, that was the W of n, that was a bound, a lower bound for the best objective value. Right? Remember that? It was just a lower bound, which may or may not be realized. Okay. Okay, so if you don't know anything better, at least once you compute your Z star, you know how to get the X star solution by simply finding a composite neighborhood representation. However, there's a much easier way to do this than that. So when I give you the easier way, you might want to question, well, why did we actually bother looking for all this neighborhood composite representation, etc.? Well, the reason is, once you have a good technique, a good algorithm, the composite neighborhood algorithm is a good algorithm. Once you have a good algorithm, the insights you've got, actually, it can be used as a theoretical tool to actually get to the result you want to get at, okay? However, we can do better than that. So, computing X star without having to use the sequential intersection procedure. SIP, or sequential intersection procedure, is the algorithm which constructs the composite neighborhood, if you recall. Okay? So I'm going to focus on two. I missed one thing here. There's supposed to be a less or I less or equal to j here, because we've got that all the way in all other previous expressions. So I forgot it here for some reason, but it should be there. And what I'm going to do now is to compute the maximum of the alpha ij's by taking the alpha less than j separately from the alpha I less than j case separately from I equals j case. Okay? So z star is going to be equal to the maximum of z1 or z2, because that's how we did it. Okay. How much is alpha I? It's ai. Hence, z2 is the maximum of the AIs. That's it. Okay? That's simple stuff. If Z star is defined by Z2, which happens to be strictly larger than Z1, then Z star is actually equal to some AS, which happens to be the maximum of the AIs, and what is the natural conclusion here? Which may not be too natural for you, maybe. I don't know.
Vs is a sensor.
Yes. In this case, whenever Z2 is actually greater than Z1, actually you can also include equality here. There's no problem with that if you wish to do that. Then whatever index S realizes the value of Z star, that vertex gives you the optimal solution. Why? Well, it's really not too difficult. Let's see if we can actually justify this as a natural statement.
there is a single point, so the intersection must be the single point, VS.
Okay. So you're saying that the radius Z star minus AS over WS, well, Z star is equal to AS, so this is going to be 0. Hence, the particular constraint associated with Vs is supposed to be less than or equal to that number, which turned out to be 0. Now the distance will be less than or equal to 0 if and only if x is actually equal to Vs. So the only solution you have for the constraint associated with vertex Vs is the point Vs. And that point will be feasible to all other constraints. Why? Because of the way we picked Z star. Z star permits a feasible solution, and that particular feasible solution for that particular constraint has to be feasible for the rest of them. Okay, so that point has to be feasible because Z star by choice or by construction is the smallest Z, which permits a feasible solution to the constraints. Okay, now let's focus on the second case. If Z is, or Z star is defined by Z1, and if that's strictly greater than Z2. In this case, there are two distinct indices. Such that Z star is equal to Z1, which is equal to alpha ST. S is different from T in this case. So if you just look at the constraints associated with those two vertices, and if you try to construct a feasible solution to these, that should also be a feasible solution to the rest of the constraints because of the choice of Z star we have. So the constraints for S and T give this, which when added up give the distance between xmvs plus xmvt less or equal z star minus as over ws plus z star minus at over wt. I'm trying to find a feasible x. I'm trying to get there. How much is the right side? The right side is simply z star into 1 over ws, 1 over wt, minus as, ws, at, wt. How much is z star? Z star is alpha st. So if you continue your equalities, that last expression is equal to alpha st for z star. And that alpha st is how much? dvs vt plus as over ws, at over wt, divided by 1 over ws, 1 over wt. The whole thing I wrote here is simply my z star, okay? Times 1 over ws, 1 over wt, minus asws plus atwt divided by wt. Now, of course, you can see from here that that cancels with that. What remains is, well, this goes with that. So what remains is the distance between Vs and Vt. So the sum of the distances x to Vs plus x to Vt is less or equal distance, direct distance between S and T. But we know that by triangle inequality, this is actually less or equal this distance. This portion is by triangle inequality. The rest is simply using the definitions of all these things. So obviously, the lower and the upper bound being equal means everything is sandwiched. Again, equality. So, implying that all inequalities in this series of expressions, well, there's only one inequality actually. That inequality must hold as an equality. The inequality holds as an equality accordingly. X, any feasible x, is the point on the unique path connecting Vs and Vt that satisfies what relationship? This thing plus that thing is equal to that. So it's the unique point on the path connecting Vs and Vt. Why is it on the path? Because the direct distance is equal to the indirect distance between Vs and Vt via point X. If you're going to have equality here, then that point has to be on the path. If you're off the path, of course, the inequality will be strict. Okay? So that portion comes from there. It should be on the path. Number two, this thing has to be equal to that, because that upper bound, this is also equality now. Okay? That has to be equal to that. This has to be equal to that. Okay? So that satisfies distance, let's call it x star here, is the point x star on the path that satisfies the x star Vs is equal to z star minus ASW divided by WS, and dx star Vt is equal to z star minus AT over WT. Actually, there are two inequalities, so you might want to switch this V to every again. Sorry about that. For some reason, I did not see the first inequality there. There are two inequalities. Okay. So the equivalent way of saying this is if you just multiply the weight with the distance and add the addend, we're talking about x star being the unique point on the path such that z star is equal to Ws dx star Vs plus As. And the second one gives you the same thing, so z star is also equal to Wt dx star Vt plus At. And both give you the maximum of Wi dx star Vi plus Ai because z star is the alpha st value, which is the bound. Okay? All right. So what do we do to find x star without having to compute the composite neighborhood intersection? All you have to do is you compute z star. If z star is given by z2, the first case I discussed, in that case there is a particular vertex that supplies that value. You just locate your x star on top of that vertex. In the second case, z star is defined by two distinct vertices. And these two distinct vertices are the ones actually whose weighted distances define the value of f. Okay? They are the most critical vertices. In that case, you simply focus on the path connecting them, and you find the unique point whose weighted distance to each vertex on that path, not on that path, but to each critical vertex of the pair, are equal. Okay? So that's the second case. We discussed some of the special cases, but when all the weights are unity and all addends are 0, what was the specialty about this? Huh? Yes. Then this method will give you the center. Well, when AI are 0, the addends are 0, the first case, or Z star being equal to Z2, will not occur because they are all 0. Okay? So it will be this case that applies. When this case applies, then Z star will simply be equal to alpha ST, but the definition simply says that the addends are 0, so there's a 0 here, divided by 1 over 1 plus 1 over 1. So this becomes 2 here. It's the longest path divided by 2. It's longest because it's the maximum of these. Okay? All right. And when addends are present, either some addend will be the largest, in which case Z2 will supply Z star, in which case you place on top of that vertex, or this case will apply. Again, you will then find the longest path together with the addends extending both ways. Okay? All right. If you don't have any questions, I guess we can stop here. I'm going to cover the nonlinear case next time.